Very good afternoon to one and all. Is it audible? Hello.
Yes, sir. It's audible,
Yes, sir,
sir.
Doctor. Is it with audible?
Okay, thank you. Yeah, now I would like to introduce the session 10 speaker, Dr. Pullarao Garu. Dr. Pullarao Garu is currently working as an assistant professor in the Department of Mechanical Engineering, IIIT Design and D&M, Kurnool from March 2019. He did B.Tech in Mechanical Engineering from JNTU College of Engineering, Anantapur, and both M.Tech and PhD in Thermal Engineering from IIT Madras. He has a total experience of 9 years, out of which three and a half years in teaching field, and remaining in industry field, which includes the software and the mechanical industry. His research areas include heat transfer and fluid flow, experimental and computational, thermal management of electronics, and optimization studies. In addition to he is involved in several administrative positions at IIIT D&M Kurnool, which includes faculty in charge central stores and purchases IIIT D&M Kurnool from 19th August to 2020, and worked as a head of the Department of Mechanical Engineering IIIT D&M Kurnool, and PhD admission in charge, and he worked as a BTech admission in charge also. Now I request Dr. Pullarao to address the participants.
Good afternoon, sir, and good afternoon to all the participants. So, thank you for introducing me, Kondareddy, sir.
Thank you, sir.
So, just a minute, I'm sharing my PPT.
Yeah.
So, are you able to see the screen, sir?
Yes, yes.
Hello?
Yes, it is visible.
So, am I audible clearly?
Yes, it is
Okay,
audible.
fine.
Okay.
Okay. Just a minute. Okay, let me start. So, I hope the screen is visible.
Yes.
So, I think so. This is the last session of this short-term training program. So, the topic for today's this session's discussion is impinging jets. So, for the thermal management, so like we'll discuss whether impinging jets can be used for a particular field or all the fields. We'll discuss about it. So, myself, Dr. Pullarao, I'm working as assistant professor at IIIT DM Kurnool. So, regarding the remaining details, Kondareddy sir might have given you. So, let us go to details about the today's topic. So, the mainly like the presentation is oriented mainly towards my PhD topic. So, I have not chosen any something a topic different. So, this whatever the discussion I'm going to take part here, it is entirely my PhD study. So, the outline of the presentation is introduction, followed by a review of literature, a research outline, what are the experimental details, and experimental studies conducted. So, my PhD study was entirely on experiments. So, I'll be taking you to the experimental part details and how the experimental setup was built and what are the different studies we have conducted. So I'll be going to discuss those things. So let us come to the introduction part. So thermal management. So during this all 3 days session, people might have discussed about thermal management. So you might be already clear with that what is meant by thermal management. Just for the sake of completion, I'm again going to recapitulate this thermal management. So it is a crucial bottleneck in various engineering applications where high power densities are involved. So any field has to emerge or it has to develop. There are some constraints are there. Out of that one constraint, one is the thermal management. So I'll give some example where this thermal management is very crucial. For example, automotive power electronics. So power electronics, for example, whatever the laptop we are using, mobile phone, or some other devices. So their thermal management is very important. Apart from that, radars, space application, gas turbine blade, automotive vehicle engines, metallurgical applications. So if you see these examples, you can see thermal management is not limited to or confined to a single field. So there are a lot many fields in which thermal management is required. So here the main challenge is the functioning and reliability are constricted by the ability to dissipate efficiently. For example, let me take the example of a mobile phone. So I have purchased a Apple phone. It is costing 50,000 rupees. So if I search in the market, same features will be available with 6,000 rupees. Some China person might have fabricated that mobile phone. China phone I can get for 6,000. Apple phone 50,000. Why this difference is coming? Because of some features. So among the features which is distinguishing this China phone and Apple phone is one is thermal management. So in Apple phone, if you talk for even two hours or also, you will not feel that mobile is not heated. But when you speak in 10 minutes or 15 minutes in China phone, you will feel very hot mobile. So you can't speak, your ear will be burning. So the China phone is poorly managed with respect to thermal management. So apart from that, even you see electronic industry also. So they are going for i3 processor, i5 processor, i7 process. They can go i9 processor like that. So they can go up to the technology has increased a lot, but so they are limited with respect to the thermal management. If you observe some Intel website or somewhere, if you choose a particular processor, there it will be mentioned what is the maximum temperature allowed, what is the junction temperature, it will be mentioned, and what is the heat dissipation level of that chip. So there the challenge comes for the electronic engineers. So now we can't say like we can't separate this mechanical engineer and the electronic engineer, because coordinately both has to work for designing a new chip. Otherwise, if electronic person only design the electronic chip, he may be successful in his motto, but when it comes to reality, he will be failure because so much about thermal management. So therefore, so now it has become interdisciplinary field. So electronic application also, like so whenever we are designing some electronic components, thermal management has to be taken into consideration. As a result, there is an ever increasing demand for efficient cooling techniques, which has attracted the attention of many researchers over the decades. So this thermal management thing is not new one. So this is there from long back, some 50, 60 years. So nothing we are we have not invented anything or we have not discovered anything. Whatever the previous researchers has done, we are adding plus delta x to that. So we are not going something, we are not reinventing the wheel or something. Whatever is their existing technology, we are adding something delta x to that. So if you come to different cooling techniques or thermal management techniques, so thermal management, it is not only confined to cooling. So sometimes it can be for the applications of heating also. So let us confine our discussion to cooling techniques. So active cooling and passive cooling. So what is meant by active cooling? So if you take a desktop computer, so their CPU is there. So in that one fan will be there. The purpose of the fan is to cool the processor or some heat generating elements. So here the cooling is done by some fan. So fan has to run means we have to supply some electricity for that. So So in active cooling technique, the cooling medium is supplied with the help of some external mechanism. For example, compressor or blower or fan. So those are required for supplying the working fluid to cool the hot object. Some examples: active cooling technique, forced convection with air or liquid. So in forced convection, I'll be sending the air with some fan or some blower. So impinging air jet or liquid jet. So this is what we are going to focus now, impinging air jet. So impinging air jet also is like some external agency is required for sending the air, spray cooling, thermoelectric cooling, refrigeration system. So these are the active cooling techniques. The cooling will be provided with the help of some external mechanism. If you see passive cooling, natural convection with air. The natural convection with air, we will not supply any external power for running this device. Heat pipe, phase change based cooling, thermosiphon. I think a few of the techniques were covered in the previous lectures. So phase change based cooling, heat pipes. So like that, a few things might have been covered earlier. So let us not go much details into that. So now I am focusing my attention towards impinging jet, and I am confining to only air jet only. So jet can be liquid jet also. Let us see what is meant by jet. What is impinging jet? So jet, a stream of fluid issued from a nozzle with high velocity. So in general, nozzle means we say it is a small cross section area. So whenever some fluid is coming with a small cross section area, just for example, you take continuity equation, A1 V1 equal to constant. So if area is becoming small, volume will become higher. So by reducing the area, I am able to increase the volume. So that is the motto of jet, a stream of fluid issued from a nozzle with high velocity. So based on the relative direction of jet with respect to object of interest. So my jet will be there. I want to cool an object. So how they are oriented with respect to each other. We are classifying it as normally impinging jet or impinging jets. Nothing but they are perpendicular to each other. Oblique jet. So instead of having 90 degrees, some other angle, maybe some 30 degrees or 50 degrees or 60 degrees. Wall jet. Wall jet means pass parallel to the object of interest. So both will be parallel to each other. So there is 0 degrees between them. So if it is 90 degrees, it is normal impinging jet. If it is parallel, it is called wall jet. If it is between 0 to 90 or some other angle, it is called oblique jet. So impinging jet. So just I have given explained so previously. Just you see so there is a red plate is there. That is the plate I want to cool it. So it is getting heated by supplying some heat flux. So there is a jet coming from the pipe nozzle. So nozzle, I told, jet will be coming out of the nozzle. Nozzle can be some orifice type nozzle or some pipe nozzle or some other nozzle. Different types of nozzles are there. So just I have taken the example of some pipe nozzle. Simple thing, just a small pipe is there, from that air is coming. That is a pipe nozzle. So the jet is coming in vertical direction. So the impingement plate is horizontal direction. You observe it is 90 degrees. Therefore, it is called impinging jet. So what are the features of it? This impinging jets provide high heat and mass transfer rates. So this fact I am not telling. So previously, so many researchers have identified and they have explored and they have listed this high heat and mass transfer rate, easy to adjust the location of interest and cool the impingement surface. For example, I am having impingement plate, bigger impingement plate is there. My jet is there, smaller cross section is there. For example, the entire plate may not be subjected to the same temperature. A particular location may be at higher temperature, another location at lower temperature. So the advantage with this thing is I can orient my jet wherever the hot spots are there. For example, the hot spot is at right side. I can direct my jet towards right side direction. Center, I can orient my jet at midpoint. If it is located at hotspot is at left side, I can orient my jet towards left side. So that is the advantage with jet. If it is a normal forced convection, so the entire surface will be subjected to the same amount of fluid flow. So, but here in case of jet, I can adjust my location of interest. So that is another advantage. So because of this high heat and mass transfer, easy of adjustment. So a remarkable attention since last 5 decades in various fields for cooling, heating and drying process. So these jets are not only used for cooling purposes, so they can be used for heating purposes and for some drying applications. And one more point you should keep in mind: the last 5 decades, this impinging jets is not the new field or something new. So the concept of impinging jets, it is there from long time. Maybe what we are doing nowadays is we are changing the application in which the impinging jet can be used. So this is not new field. Impinging jets is not new field. We are just changing the application. So in recent times, jet impingement cooling is becoming increasingly popular in thermal management of electronics. That's what I'm telling. So in last 10-20 years, so these impinging jets are widely used in thermal management electronics. So earlier also it was used, but in different fields. So just observe different fields in which these impinging jets are used. So for cooling application, heating application, drying application. So you see gas turbine blade cooling, electrical equipment cooling or electronic equipment cooling. So their chips are there, chips are getting cooled. Again, you see drying of paper and textile industry. So there, once some paper or textiles are manufactured, so they will get hot, like little bit higher temperature. We have to cool them. Rocket launcher cooling, processing of steel arm glass. So we can see with this picture, we can see these impinging jets have scope in wide variety of applications. Cooling, heating, drying, as well as in different applications, different fields. So let us see the structure, like how impinging jets, physics associated with these impinging jets. So before going into its application part, let us see the physics associated with this impinging jet. I have taken a pipe nozzle. So through the pipe nozzle, fluid is coming. The pipe is having a diameter d. So the fluid comes out of the jet, comes out of the pipe with velocity v. You see there different regions were demarked in the figure. You see free jet region, stagnation region, wall jet region. Free jet, so you see pipe nozzle is there, there is an impingement surface is there. So in free jet region, the influence of this impingement plate is not seen. So therefore it is called free jet region. So the jet traveling after a certain distance, it is going to hit on the impingement plate. The region which is under the direct influence of jet is called stagnation region. And after hitting on the impingement plate in the stagnation region, the jet hits perpendicularly or normally. After hitting on the surface, it will move parallel to the surface. Then it will become wall jet. So once the fluid is flowing over the plate parallelly, then it will form boundary layer formation that we can see left hand side. Boundary layer formation is there. So boundary layer growth will be there. So that is what the impinging jet physics. So free jet region, stagnation region, wall jet region. So let us go a little more further details about this free jet region. So flow region in free jet region. So just the nozzle is having a diameter of d or w. If you see, as the jet is moving longitudinally, or the jet is moving in the surrounding surface, if you observe, laterally its diameter is increasing. So there is a lateral distribution of when it is moving like longitudinally, lateral also there will be some spread of the jet is there. If you see here, so different regions are there: potential core region, developing zone, fully developed zone. You may be come across this laminar flow through pipes. There also this type of regions will be there. So that is somewhat different. But here, potential core region. In this potential core region, there is a cone is there. In that cone, the velocities are equal to the velocity at the nozzle exit. So as you see away from the potential core region in lateral direction, there will be the velocities will be lesser than the potential core region. Apart from that, as the jet is moving forward, the lateral spread of the jet is increasing. So that means that you could see the area of the jet spread in lateral direction is increasing. So up to certain distance, potential core region exists. After that, some transition region will be there, that is called developing zone. After that, fully developed zone. In the fully developed zone, so it is entirely having different velocity profile, but the profile will be same as the jet is moving in forward direction. So coming to the literature part, so any research, it is very important. Without any literature research, you can't become a good researcher. So the purpose of doing literature review is, first we should know what people have already done. If people have already done, what is the need to do the same thing again? So what is the need to reinvent the wheel again? So first we have to, the motto of doing literature review is to first understand what previous researchers has already done. Second thing, how they have achieved few things. For example, some people might have done by computational studies. Some people might have done analytical studies. Some people might have done experimental studies. We can understand how a problem can be tackled. What are the different methodologies that can be adopted? Next, we have to find some gaps. So everybody cannot do everything. So therefore, there will be some gaps will be there. So those gaps we have to identify. Based on the thorough literature, we have to identify the gaps, and accordingly we have to plan our research topic. So that is what, for that thorough review of literature is important. So let us see some. So what are the literature I am going to explain? It is not the only papers I have read. So there are some hundreds of papers we have gone through as part of PhD work, but a few papers only I am providing you. So first let us see Quinn. What he has done with an increase in the aspect ratio of a rectangular slot. So rectangular slot, as I already told, the nozzle can be pipe nozzle or orifice nozzle, or the nozzle can be square shape, or it can be rectangular shape, or it can be triangular shape. There could be so many varieties of shapes will be there. So here rectangular slot. So aspect ratio. So if you take a rectangular block, it will be having a length, it will be having width and height. So the ratio of width and height, it is called aspect ratio. So by varying the width and height ratio, they have conducted the studies and they observed some heat transfer performance was improved. So by taking the rectangular jet, by varying the parameters width and height ratio, so they observed and heat transfer performance is improved. Again, next study. So by creating intermittency in the jet flow, it is like on off type of flow. It is not like not having continuous flow. By creating sometimes for 1 second it will be on, for 1 second it will be off, 1 second on, off. Such type of flow they created. They conducted the studies and observed heat transfer is increased. Again, next study, excitation in the jet flow. They have created some excitement in the jet flow, like by creating some vibration kind of thing, and conducted the studies, observed heat transfer improvement is there. Next study, Lee and Lee in 2000. One study is elliptic jet with increase in the aspect ratio. So elliptic jet, as I already told, it could be rectangular or square or circular. Even elliptic jet can be there. Elliptic jet means, elliptic shape means it will be having major axis and minor axis. The ratio of major axis by minor axis, it is called aspect ratio. So by varying that ratio, studies were conducted. So next, another study, Lee and Lee. So nozzle exit configuration. So by using some sharp edge nozzle, standard edge nozzle, square edge nozzle. So these are the different types of nozzle configurations they have used and conducted the heat transfer studies. So again, Lee et al. In 2004. So they have varied the nozzle diameter and observed how the heat transfer performance is there. Next, confined and unconfined jets. Again, so depending upon the type of jet, we can have a confined jet, unconfined jet. So that is one variation of a type of jets. Another thing, unsteadiness in the jet flow. Instead of having a steady flow, it is like by having some triangular profile kind of thing or rectangular profile kind of thing, or some wavy kind of profile thing. So by creating unsteadiness in the jet flow, so they have conducted the studies and observed heat transfer performance is improved. Again, so in 2010, the studies conducted were by varying the inlet geometry and aspect ratio. Inlet geometry means like if it is a rectangular jet, if it is a square jet, if it is a circular jet, if it is an elliptical jet. So they have conducted these studies and observed that which one is performing better. So those studies were conducted. The next, some piezoelectrically driven synthetic jets compared with steady jet. So like this, different variation of jets were used. So the list goes on. So various flow control techniques have been employed. So flow control techniques, just like by creating the excitation in the flow, or by creating the unsteadiness in the flow, or by varying the shape of the nozzle, or whatever it may be, by changing the flow pattern, that is by flow control. Heat transfer studies were conducted. So in some studies, heat transfer performance was reduced. In some studies, heat transfer performance was improved. So whichever is giving better performance, they have focused more on to that heat transfer enhancement phenomena. So it is not like you should keep in mind that. So research always should not give positive results. There's sometimes there will be given negative results also. You anticipate that heat transfer enhancement will be there. So you will get heat transfer reduction will be there. So that is also on research. So you should tell, you should not do like this. If you do like this, so it is not advantage. It is not like always you should tell advantages. There are situations you should tell disadvantages also. So some studies given heat transfer enhancement, some studies give poor heat transfer. So those heat transfer enhancement things will be discussed further. So next, apart from that, another set of studies were conducted where, so instead of having a normal nozzle, so they have conducted like perforated plate. So instead of having a plain nozzle, they have put some perforation kind of thing, like just like you are having some a sieve kind of thing. There will be some so many holes will be there. Such type of nozzles were used. And another thing is delta tabs at the nozzle exit. Instead of having a plain nozzle or circular nozzle, they have put some tabs at that. They have created some disturbances at the nozzle exit. And again, they have put some twisted tapes inside the nozzle. Some tapes were inserted in the nozzle. And another thing is Gori and Petrasi, metallic grid. So by putting some metallic grid, so in 2015, they have used some fractal grid. So in 2016, some chevron nozzle. So whatever here it is, what is, for example, you fix some shape, for example, circular thing. So by varying, by creating some some obstruction in the flow, by using perforation plate. So many studies have been conducted to enhance the heat transfer performance by adopting flow blockage techniques such as installing wire screen, grid, fractal grid, etc. within the nozzle. So by creating some flow disturbance or flow blockage, they have conducted the studies. They might have used some meshes, or they might have used some fractal grids, or they have used some delta tabs. So by adopting some different flow blockage techniques, studies were conducted and observed heat transfer performance was there. So apart from that, till now we discussed how when we change the flow control means varying the profile of the nozzle. Another thing is flow blockage. In flow blockage, like if I block the flow, how the performance was there. Apart from that, this we have concentrated at jet side. So what about the impingement side? So if we create some disturbance at the impingement side, what will happen? So in the year 1992, the study conducted was millimeter scale fins on the impingement surface was there. So I told, so there is there is impingement surface is there is a nozzle is there. So till now we discussed about nozzle. So now impingement surface. So there, if some fins are used on that millimeter scale, not large scale fins, some millimeter scale fins are used. Whether heat transfer performance is improving or not. So they observed, and it is observed to be improved. Again, some roughness on the impingement surface. If we create some roughness on the surface, what will happen? Next, microstructure surface. Microstructure, not milliscale. Microstructure surface. Next, session. Nanostructured surfaces. And in 1993, some modified surfaces, some 6 different types of modified surfaces were used. So next in the year 2002, Eckert and Kontrovich, dimpled surface. So by varying the profile of the impingement surface, by adopting the fins or microstructures or nanostructures or roughness, or creating some profile on the surface or creating some dimples. So what is happening to the heat transfer performance? So many studies have revealed that impingement heat transfer can be altered. It could be increased or decreased by adopting modified surfaces. So with this background, I have formulated my research topic. So the common feature is flow disturbance. So if I create flow disturbance at the nozzle side or orifice side, if I create the flow disturbance at the impingement side, I adopted some rough surfaces at the and some microfinned surfaces at the orifice surface side, some distributed orifice fitted with wire mesh. So what is distributed orifice? We will see later. What is with mesh? That we will see later. So finally, I compared these things. So by creating the flow disturbance at orifice side or at impingement side, how the heat transfer performance will be there. So my focus is mainly towards the enhancement in the heat transfer. So we will list after conducting all these studies, we will tell which case heat transfer enhancement will be there, in which case heat transfer reduction will be there. We have to list out all those things. So whichever is required. My motto is to heat transfer enhancement. We have to focus on those enhancement studies only. So details of the experimental setup. I have already told. So my entire study is experimental. So as part of this, I have built this left-hand side experimental setup. So this I have developed from scratch. So nothing was there. I have developed from on my own. So this, let us observe this right-hand side figure. I have already told impinging jets. It is one type of active cooling technique. Active cooling technique means I should provide some external mechanism to provide circulation of working fluid. So here I am using air. So air has to flow. For that purpose, I should have some external mechanism. That is what here used is air compressor. You see right hand side figure. That is air compressor, part 1. So from the surrounding air will be sucked, the compressor will compress the air. So once we compress the air, what will happen means, so what are the water vapor in the air, it will get condensed. So I have to filter that condensed water. For that, second part, filter regulator unit is there. For example, we are taking surrounding air, that may be having some dust will be there, some water vapor will be condensed. Those things will be removed with the help of filter regulator unit. Next comes the dehumidifier. So if this filter regulator unit almost remove the water vapor. If any little bit traces are left out, so those things will be removed with the help of dehumidifier. So next, there is a digital pressure gauge to record what is the pressure that is I am sending into my mainstream. So because once I compress the fluid, it will be pressure will be raised. It is not atmospheric pressure. So for that purpose, I should know what is the pressure that is going into my mainstream. So with the help of digital pressure gauge, we are recording it. So next, part 6 is there. 2 are there. So they are called rotameter. The purpose of the rotameter is to measure the volumetric flow rate. So there are 2 rotameters are there. So each rotameter will be having particular range. So if I want to go for higher range, so those 2 rotameters, one is in the lower range, another is in the higher range. So if I have to go to higher range, I have to close the lower range thing. So for that purpose, needle walls are there. So by controlling the needle walls, I can control the flow through the lower flow rate rotameter or higher flow rate rotameter. After that, again those two will be merged and it will be entering into that horizontal pipe section. There some 7 is there. So the fluid is coming with so many zigzag portions are there. Some it will be coming to so many pipes. So there will be some turbulence eddies will be created. We have to reduce the turbulent eddies. For that purpose, some settling, I mean, some widescreen mesh will be arranged. If some large turbulence eddies are there, it will break those turbulence eddies and it will make sure that flow will be straightened. Again, settling chamber will be there, so the flow will be almost become laminar flow. So next, number 9, it is thermocouple. So the purpose of this thermocouple is to measure what is the air inlet temperature. So what is the temperature of the air that is coming out of the nozzle as a jet. So next 10, there is a provision for pressure tap. I will tell why that provision is provided. Next 11, that is the orifice plate. I already told. So I am creating some modification at the orifice plate side. So that orifice plate, that 11 thing will be, I'll be wearing that whatever that part 11. So throughout my entire list up to that 9, 10, up to that part, everything is fixed. That part 11. So that is the variation thing. So next, if you observe 12th, that is the impingement plate. So on that, air will be coming out of the orifice plate and the jet will be hitting on the impingement plate. The impingement plate backside, there will be some heater will be there. The heater will be supplied with some DC power supply, that is 14. So 13. The purpose of 13 is to make sure that the impingement plate, it can move up and downwards, back and forth with respect to the orifice plate. It can go closer to the orifice plate or it can go away from the closer plate. That for that purpose, some traversing mechanism is provided. The next 15 and 16, what are the temperatures we record? So those things will be recorded with respect to data logger and it will be connected to computer. So our focus should be confined to 11 and 12. 11 is the orifice plate, 12 is the impingement plate. So by making the modification at the impingement plate, what are the heat transfer phenomena occurring? Or by modifying the orifice plate, that is 11, what are the things that we are going to achieve? So 11 and 12 are the prime focus of our study. So out of this entire setup, 11 and 12 we are going to focus. So since it is experimental study, so we should list out what are the instruments we have used. So there is a differential pressure transducer. So to measure the pressure drop across the orifice plate, you see that pressure tab 10 will be there. So differential pressure means two ends will be there. One end will be connected to the location at 10, another will be connected between, just it will be kept open between nozzle and plate to make sure that what is the pressure drop across this orifice plate. As I already told, I will be wearing different varieties of orifice plates. So therefore, to compare with a particular type of orifice, what is the pressure drop across the orifice plate? If some other type of orifice plate I use, what is the pressure drop? For measuring those pressure drop, I have differential pressure transducer, single wire constant temperature anemometer. As I told, there is airflow is there. When the fluid is flowing as a jet, the velocity can vary, turbulent intensity can vary. We have to measure those things accurately. We have to use some instrument that is called anemometer. So since we are conducting the heat transfer studies, so heat transfer studies means temperature has to be estimated. So that is measured with respect to K-type thermocouple. So I have thermocouples. So thermocouples will come in 2 wires. So those 2 wires we have to join together and we have to form some junction. So after forming the junction, we should check how it is performing. So any instrument we have to calibrate it. So otherwise, calibration is must for any instrument. Calibration means that is checking with respect to standard value. So what are the thermocouple? So those fabricated in the laboratory, we have to check whether they are giving correct readings or not. For that purpose, so a constant temperature bath is used, that is made of Julabo. So that is to calibrate the thermocouple. The bottom one is flat heater. So I told impingement plate will be heated with respect to some supplying heat, some supplying power. So that is done with by providing some flat heater. So that is some mica sheet is there inside, some nichrome wire is winded. So and those two, whatever we could see, like 2 wires coming, those are plus and minus wire. Those will be connected to the power supply thing. So inside that nichrome wire is there. By switching on the power supply, so current will be flowing to that nichrome wire. The nichrome wire will get heated. The heat will pass through this mica sheet, and this heat will be given to that impingement plate. So any study, we should have some parameters. So we should know what are the parameters associated with it and what are the expressions for the mass flow rate of the jet fluid, density multiplied by volumetric flow rate. Volumetric flow rate that we will measure with respect to rotameter. If you multiply by density, you will get mass flow rate. Apart from that, pumping power consumption of the jet across the orifice plate, the delta P, it is the pressure drop across the orifice plate that we told. Pressure drop across the orifice plate is delta P we will measure. If you multiply with volumetric flow rate, we will get what is the corresponding power consumption with respect to pumping power. If some pressure drop is there, it is associated with some power consumption. So those things. So that I have converted to dimensionless orifice to target distance. So the distance between orifice to target. So that is Z, and we are non-dimensioning with respect to some B. That is the width of the orifice, Z by B. So if I use different, for example, if I use B as some 2 meters, I mean 2 mm, so Z by B equal Z by 2, some so and so value will come. If I use B equal 4, Z by B equals so and so. So different values will get. We have to normalize it. So for that purpose, dimensionless number will be taken. Heat flux. So whatever the heat we are supplying, so there will be some losses will be there. We have to account those things and divide by area. We will get heat flux. Nusselt number calculation. So next, width of the orifice plate. So here, so our motto is to make sure that heat transfer enhancement should be there, but at the same time, power consumption, pumping power consumption should be less. So what are the pumping power consumption is the input we are giving. Heat transfer enhancement is the output we are getting. So if output is increasing, input should not increase. So we should make sure that at the lower, by putting less cost, we should get more results. So we have to put some optimization with respect to this thing. Output and input should be some balanced things should be there. So uncertainties in the measured quantities. So any experimental study or equipment is prone to errors. So any experimental study without reporting the errors, it is incomplete. So we have to list out what are the measured quantities. Some measured quantities will be there, some derived quantities will be there. What are the instruments you use? With respect to those things, we will get measured quantities: temperature, voltage, current, velocity, pressure drop, pressure. So those are the different quantities, measured quantities. What are the error or uncertainty associated with those measurement? So they are reported. Some will be reported value, some will be reported with respect to percentage basis. Different variation of reporting the results will be there. So apart from this, what are the derived quantities? For example, heat transfer or Nusselt number. So those things also prone to errors. Those are derived quantities error. So those things also we have to estimate. So validation of the experimental setup. So people may think so only CFD studies should be validated. It is not wrong. It is not correct. Even sometimes experimental setup also need to be validated. So since I told, so this is the setup built by me newly. So I don't know how far I'm constructed my setup properly. For that purpose, I should check whether my experimental setup is correct or not. For that purpose, I have to check my experiments, compare the results with previously published results, and observe whether they are matching or not. If they are not matching, I should ensure that something is a mistake with respect to my fabrication. I have to introspect and I have to plan my setup accordingly. So if you see like two figures are there, mean velocity and turbulent intensities. If you see the left hand side figure, so the mean velocity is the what are the black line, it is the validation, my studies. That pink line, pink dots, that is the research, like what are the literature. So I observed, and both the normalized velocity is more or less matching, and we see the turbulent intensity. The same trend is followed, but the values are not matching. So, but when we observe the literature, so some different people who have conducted this type of validation studies of their experimental study, and they have reported that as long as this velocity is matching, there is no problem. This turbulent intensity can be varying. It depends upon the surrounding condition, and so many factors will come into picture. So therefore, if the profile is same, there is no issue. It need not be turbulent intensity, need not match. So therefore, with that, with the literature available, I have concluded that my setup is okay, acceptable thing. So then I have started my experimental studies. So I have conducted different types of studies. Let me start with study number 1. Impinging jet issuing from distributed orifices. What is meant by this distributed orifices? So 3 different types of configurations were used. So if you see here, configuration 1, single orifice, 4 orifice, 9 orifice. If you see the outer area, that is 4.6 by 4.6 mm square. Then case A, that 4.6 by 4.6, it is having single nozzle. In case B, in the 4.6 by 4.6, I have put 4 nozzles having 1.9 and into 1.9. So the remaining part, that is 0.8 gap between those two, it is solid part. So coming to the case C, so there are 9 nozzles are accommodated in the same 4.6 area. So if you observe what is the effective flow area, so we have defined some parameter called flow area ratio. We compared with respect to single orifice. For the case of single orifice, it is 1. For the case of 4 orifice, it is 0.682. For the case of 9 orifice, it is 0.425. So out of the 4.6 by 4.6 area available, in the case of 9 orifice, only 42.5% is through that only fluid is coming. The remaining part, it is solid part. The fluid will not come outside that. So this is by creating this flow area disturbance. So these are the orifice plates we have used as part of our study. So these are the photographic views of those things. So to give you a feel of that, what is actually happening. So we can go for even like 4, 9, 16 also we can go. But the problem is like one orifice width is 1 mm. Like going for a little below that 1 mm, like fabrication has become difficult. If you have to go for computational studies, we can go for a maybe 0.5 mm also. So when we are doing experimentals, fabrication, there are so many complications with respect to fabrication. Even for putting 1 mm, that is the square hole also, it has become very, we have to go for some EDM techniques. If I go to even below that 0.5, again we have to go for sophisticated fabrication techniques. So that's why I have confined up to only a 1 mm thing. So as part of this distributed orifice, so in the study 1, like fixed mass flow rate condition. So I have fixed whatever the, whether it is single orifice or 4 orifice or 9 orifice, whatever the fluid flow I am sending, it is fixed. So then I observed what is the happening to the velocity. If I observe that is black line, it is the case with single line, single orifice. That colored one, red and blue, they are with 4 orifices and 9 orifices. That blue one in the mean velocity thing, it is having higher velocity when compared with a single orifice. Again, if you see the turbulent intensity, that blue one, that is in the 9 orifice scenario, it is having higher turbulent intensity because 2 reasons are there. First thing, so the flow area has reduced. Therefore, so if I fix mass flow rate M equal to rho AV, so area is reduced, therefore volume will increase, mean velocity is increasing. Again, if you see the how turbulent intensity is increased, the flow has to go through, earlier single orifice, it has to go through 1 passage. Now it has to go through 9 passages. So the flow has to distribute in 9 directions. So obviously there will be disturbance in the flow. So obviously when disturbance in the flow is there, turbulent intensity will be increased. So these are the phenomena happening behind. Velocity is increasing, turbulent intensity is increasing. So because, so these are the advantages. Velocity increases, turbulent intensity increases. Okay, good. But what happened to the pressure drop across the orifice plate? I have put orifice plate. If I take single orifice scenario, what is the pressure drop across it? Multiple orifice, what is the pressure drop across? Let us see the last one, 7.4 scenario. Pressure drop 41.5, 119.4, 226 Pascal. You see like almost 5 times it is there. 41 and 226, it is almost 5 times it is there. Pressure drop has increased 5 times. correspondingly the pumping power is also calculated. It is 26.4 into 10 power minus 3, not 10 power 3, 26.4 into 10 power minus 3, that means 0.0264. Higher side will be 0.143 watt. So 0.143 watt, it is a very small value, even though like when you compare like percentage wise, it may be some 5 times, but magnitude wise, it is very small. So whatever the pumping power consumption, it is increased, but the value is slightly more only. So this can be okay. We can leave it. So what is happening to the heat transfer performance? If you observe that black, red, and blue lines, the blue line is having higher heat transfer performance. So just if you observe at some 3.4 into 10 power minus 4, so it is having 34 and 57% increments are there when compared with the single orifice. What is the reason? We have already observed. Mean velocity is increased, turbulent intensity is increasing. So whenever we are reporting heat transfer performance is improved, we should justify what is the reason for that. So to justify that thing, we have conducted the fluid flow studies, turbulent intensity studies. Then we concluded that because of these reasons, heat transfer is increased. So because of adopting these multiple orifices, heat transfer performance is increased. Whatever the pumping power consumption, it is limited. That is, we can neglect it. Apart from that, so that is one type of study in this case one. So another thing is same distributed orifices. I want to fix my Nusselt number on the target plate. I have fixed what is the heat supply to the target plate. I have fixed my Nusselt number. So then, for example, let us see Z by B equal to 7. Single orifice. My average Nusselt number is 38.5, 38.6, 38.5. To achieve the same Nusselt number, what is the fluid flow rate required? If you see single orifice, the fluid flow required is 7.4 into 10 power minus 4 kg per second. 9 orifice is 3.5 into 10 power minus 4 kg per second. So the amount of air required is become 50%, 50% or 40% only. For example, since it is a air, so it is freely available. If I am using some other fluid, I should have some extra fluid should be there. Apart from that, here also I am using a compressor. So I should use double, like for example 3.5 and 7.4. I have to handle, if you take single orifice, I have to handle double the amount of air flow rate. So then the power consumption of the compressor also it will increase, and I should use the larger capacity compressors. So these things are also coming to consider. If I take the 9 orifice scenario, if I go for multiple orifices, the amount of fluid required is reduced, and the compressor size also get reduced. This is also an advantage. So from these two studies, we can conclude that. So with respect to, if I fix the mass flow rate, Nusselt number can be increased. If I fix the Nusselt number, the amount of fluid required will be reduced. These two are the favorable phenomena for me, favorable scenarios for me. So another scenario, impinging jets with nozzle having wire mesh at the exit. So just you see the left hand side figure. If I place this type of orifice plate, how the mesh will be, that red portion, that is the wire mesh. So that like instead of having a plain nozzle, like simple nozzle, we are putting some wire screen meshes. They are simple wire screen meshes, just like we have taken some mosquito or like window meshes. So 3 different varieties of meshes were taken. If you observe between, I have put some steel rule between 11 and 13. You observe different number of wires are there. So number of wires will be there. Gap will be also be there between different will be there between 2 adjacent wires. So these are the normally available wire meshes. So again, we have measured the area based porosity. Like I have used 3 different types of wire mesh and one case without mesh. So again, we have measured what is the area based porosity value and conducted the studies. Again, study with fixed mass flow rate condition. So when I fix the mass flow rate, what is happening with respect to velocity? What is happening with respect to turbulence velocity? Just if you observe the green portion, that is mesh having 0.35 porosity, mesh 0.35, that is having porosity of 0.35. Mesh having lowest porosity, it is having higher velocity and higher turbulent intensity. the same phenomena, whatever I told. So when the area porosity value is reduced, that means area is reduced for the jet flow. As a result, velocity increases. Again, turbulent intensity also increases. So these are the background phenomena. Mean velocity is increasing, turbulent intensity is increasing. So coming to the pressure drop and power consumption, just to see 4.82 into 10 power minus 3 scenario, 242. That is without mesh. With mesh, 0.6, 431, 631, 784, 242 and 784, almost 3 times it is there. So correspondingly, the power consumption 1.010, 3.274, around some 2.274. So in this study, whatever the heat I am supplying, that is 43.2 2 watt. The heat I am supplying is 43.2 watt. The power consumption with respect to this mesh is 1.01, 3.2. The difference is close to 2.2. 2.2 and 43.2, around some 5% is there. So some significant value is there. We should introspect this aspect. The previously it is very magnitude is it is very small, so we did not concentrate much on that power consumption. But here it is close to 5%. So we should introspect what is happening here. So that phenomena we will see later. So here, instead of having presenting the result in a like monotonic way, like some whenever we are presenting some paper or something, we should present the same result in a different way. Previously, I have told like how I am comparing like without like single one and perforated. Now what I am taking, I have taken the ratio with mesh divided by without mesh. So here I have drawn some horizontal line with 1. So if you see the figure, all are above 1. That means, so because of the mesh, the heat transfer performance is improved. So that is the, like I have presented the result in a different compared to the previous scenario. Like it is having more than 1. So that blue one, that is mesh 0.35. It is having higher performance because it is having higher velocity and turbulent intensity. Coming to the, I told, what are the power consumption? That is a significant value. Let us focus on power consumption value and keep studies on that. So I have fixed the pumping power consumption 0.376 or let us take 1.10. So I want to maintain the pressure pumping power across the orifice plate should be same. So correspondingly, what is the required mass flow rate? What is the pressure drop? If you see, for the case of no mesh, it is 4.82 into 10 power minus 3. For the case of mesh 0.35, it is 3.10 into 10 power minus 3. So the mass flow rate is reduced. So the amount of mass that is flowing is reduced. So you see mean velocity and turbulent intensity values. You see that black portion, it is without mesh. The remaining colors are with mesh. If you observe at lower Z by B values only, mean velocity is higher for mesh. But as you move away from the nozzle, Z by B value is increasing. The mesh without mesh part is having higher mean velocity. Even with respect to turbulent intensity also, at lower Z by B values only, meshes are having higher turbulent intensities. At higher Z by B values, meshes are not having turbulent intensity higher. So with this, if you observe here, what is the heat transfer performance? When you observe at the lower Z by B values only, we can see enhancement is more than 1. But at higher Z by B values, there is a reduction in the heat transfer. So then we should not go for such type of studies. So whenever we want to focus our concentration, my constraint is fixed pumping power consumption. I should use lower Z by B values only. If I go for higher Z by B values, it is not advantageous. So that is what we have to conclude. So effect of orifice blockage element on the performance. What are the studies previously we conducted without any disturbance, with distributed orifice, with mesh. So these three we have taken and we compared. So by 3 different parameters, by fixing the mass flow rate, by fixing the pumping power consumption, or by fixing the Nusselt number. So by fixing the mass flow rate, you see that black one is without blockage or without any disturbance. Red one is with mesh. Blue one is with the distributed orifice. You see like velocity is more or less same, but turbulent intensity is higher for the distributed orifice. So accordingly, you see like just come to figure 23, just heat transfer enhancement, heat transfer performance is higher for the blue thing, that is nothing but distributed orifice, because turbulent intensity is higher for this thing. So that is the reason. Another thing, when you see the pressure drop and pumping power consumption, so without blockage it is 242, with blockage it is 431 and 491. So obviously with blockage pressure drop is higher, but when you compare this with mesh and distributed orifice, the pressure drop is little bit, like some little bit variation is there, some 10% variation is there, but heat transfer enhancement is more. So next, fixed pumping power consumption, again like at the orifice side. So I have fixed the pumping power consumption, again conducted the studies. So again this pressure drop, mass flow rate, those things were observed, and again if you see here, the performance is there at lower Z by B values only, heat transfer enhancement is there, at higher Z by B values, so these are not good for heat transfer enhancement. Again even throughout the study, if you observe that blue one is having higher performance, that is nothing but distributed orifice. In this study also, distributed orifice is performing better than the mesh. Again by fixing the Nusselt number. Again here also we have conducted the studies. So here if you observe that, let us observe that Z by B equal to 2, without blockage the flow rate required is 4.82 into 10 power minus 3. With mesh it is 3.61 into 10 power minus 3. Distributed orifice it is 3.23 into 10 power minus 3. So because of adopting flow blockage techniques, if I want to keep fixed Nusselt number, the amount of airflow required is reduced. So as a result, my compressor size also reduced. It is advantage for me. So what are the throughout all these three studies we observed? Flow blockage techniques, in some cases they are outperforming the without blockage techniques. And when we compare the mesh and distributed orifice, the distributed orifice performance is better than the mesh scenario. The physics associated with that thing also described. So next, so these three parts are associated with adopting some blockage techniques at the orifice plate. So now let us come to the part of impingement side. So I have taken 8 different varieties of surfaces. In that, baseline smooth surface, even the whatever the how good you perform smoothness on the surface also, it will be having some roughness there. It is 0.3 micrometer. So we have, and again we have created some roughness on the surface. So 3 different varieties of roughnesses are taken: 6.8 micrometer, 12.9 micrometer, 19.7 micrometer. So that is like we can't judge what is the increment in the area. So that's why I have left it blank. So roughness. Next, we have used different varieties of fins: longitudinal fin, medium fin, short, medium, tall. Based on the height of the fin, we will say the short or medium or long fin. So it is in the millimeter, millimeter scale fins. I told millimeter scale fin, 0.377 mm, 0.689 mm, 1.018 mm. So actually we did not made intentionally 0.377 mm. We thought of fabricating 0.4 mm, 0.7 mm, 1 mm. But when we actually measured, it has become like under microscopic, some sophisticated instrument. It is not 0.4, it is 0.377 mm. It is not 0.7, it is 0.689 mm. So based on the height of the fin, we have classified as short, medium, long. Another thing is concentric grooves. So that is also there. By creating some, instead of having longitudinal fins, we have created some circles on the surface. So let us see the, as part of this thing, heat transfer results of the rough surfaces. With smooth surface, baseline surface, rough surface 1, rough surface 2, rough surface 3. So just let us go see, for example, Reynolds number 9650. The average Nusselt number 57.8, 58.1, 58.4, 58.9. The increment is very minute, 57.8 and 58.9. That is very small. You can't say it is increment also. So we can say the heat transfer performance is more or less same. So in the present scenario, whatever the Reynolds number range I have used and whatever the roughness values I have used, they are not good for enhancement. So whether the roughness is there or not, it is not creating any change. So even I use a smooth surface or rough surfaces, heat transfer performance is same, because whatever the roughness we are providing, so it is not able to break the thermal bond layer. The purpose of creating roughness is to, whenever the fluid is flowing over the surface, bond layer will be formed. We have to break the bond layer and advance the turbulence region. But whatever the roughness we are providing, that is not able to break the bond layer. So as a result, they are behaving as if it is a smooth surface. So therefore, they are behaving as if all are same. So then we concluded that for the range of Reynolds number, the roughness values used are not useful for heat transfer enhancement. This is also one conclusion. It is not always we should have enhancement. Next, short, medium, long, and without fins. We have compared that black one is without fin. The colored portions are with fins, and if you see the green one, that is the tall fin, it is having highest heat transfer performance. It is having some 15.3% increment is there. The reason are, just to come back to the here. If you see the here, short fin, medium fin, tall fin, percentage area increase over the baseline case. If you see the tall longitudinal fin, the area is increased by some 36.4%. The reasons for improvement in the heat transfer, area is increased. Again, fins are there. So whenever fluid is flowing over the some passage, the fins are coming as a disturbance. Flow break will come. So laminar will become converted into turbulent. So the viscous sublayer will be broken. So there are wide varieties of reasons are there. Whether it is because of increase in the area or breaking of the laminar sublayer or early progressing of laminar turbulent region. So there are different reasons for this improvement in the heat transfer. So one conclusion is, so longitudinal fins are good for heat transfer enhancement with respect to jet impingement. So to conclude whether it is only area is the reason, for that purpose another set of study is conducted where short longitudinal fin versus concentric grooves. You see here, short longitudinal fin, what is the increment in the area? That is 13.5%. Again, we have taken concentric grooves, 13.1%. Like improvement in the area is more or less same only. So then, which is performing better? So when we observe that black one is short fin, red one is concentric ring. So both of them are having almost the same area improvement, but that concentric ring part is showing better performance. That means whatever the fin or grooves we provide on the surface, area is not only the criteria. Whatever the profile we are creating, that is also one criteria that makes the difference with respect to heat transfer enhancement. So it gives some ignition for going for further research. Like if I change the profile of the impingement surface, here I have used longitudinal fins and concentric rings. Somebody can adopt some different varieties of fins. How these performance will be, so that it opens up further studies. So the orientation of the fins or the profile of the fins on the surface makes a difference with respect to heat transfer enhancement. Thank you. So that is what as part of my study. So now the floor is open for the questions. Participants, any questions?
Participants, you
Sure.
can ask
I
questions.
have a doubt.
Yeah.
Sir, can we increase the number of RFSs go on? Or is it the optimized value 9?
No, I told that what are the 9 RFIs I have used? It is 1 mm hole size. And getting 1 mm hole size and particularly square size, it is very difficult with the normal manufacturing process. Again, we have to think about fabrication process also. For getting 1 mm hole also, it became very difficult. Like EDM, like some sophisticated techniques we have gone for. Like again, if you have to go for some 0.5 mm, again still further you have to go for that. Fabrication itself will become difficult. So you can conduct some CFD studies and you can go for different varieties of sizes.
Okay, sir. Thank you, sir.
Okay.
Any more questions?
Hello, sir.
Yeah.
Hello.
Yeah.
So why did you prefer square profile only? Why not circular profile?
Why not circular profile? Means within the same area, right? No, why not means I thought, for example, if I go for if I take some circular orifice and if I put so many circular orifices, so the orientation and For example, putting of the area cannot be used properly. If we use some rectangular type of profile or a square profile, the area can be properly used. If you go for some circular profile, the managing of the multiple holes in that is a bit difficult. And moreover, it is up to us. Like we can't say like we have to go for this thing only. One thing I want to tell: research is not something like a great thing. Like whatever is missing in the literature, we have to choose something, some area, and we have to go accordingly. You can go with even a circular thing also. I felt like this circular square thing was better for me. And I want to compare
Thank you.
with mesh scenario also. I don't have any mesh with that circular profile.
Okay, sir. Thank you, sir.
So we can choose anything. Like only thing is research means it is not like doing some not so great things. We have to show the results in a different way. What others have done, and we have to show the results in a different way. We have to find the gaps in the literature, and we have to plan our proper problem accordingly. Okay. Any more questions?
Sir,
Yeah, Pon.
in the mesh, if there are more holes, the flow will merge, right? Will there be any effect because of that?
Flow will merge means when it comes out. Yeah, it will merge.
Sure. Will there be any difference?
Yeah, it will be some difference will be. That is what to check the difference. We have measured the velocity and turbulent intensities, right? We by common sense we know that it will merge and something will happen. But as a physically we have to tell, like we have to measure something, and we should be in a position to tell what is happening. For that purpose, we have measured what is the velocity at different distances from the nozzle, and what is the turbulent intensities. Those things are measured with respect to anemometer. So that gives that whether they are merging, and if they are merging, what is happening, that will give.
Okay, sir. Thank you.
Okay. Thank you, Dr. Pularao Garu.
Thank you,
for
sir.
your
Thank you for
excellent
giving opportunity.
presentation.
Yeah.
Thank you for accepting our invitation and spending your valuable time with us. Thank you.
Yeah, thank you, sir. Thank you for providing me opportunity to give a session in this short-term training program. Thanks to the organizers as well as the participants. Thank you all. Any questions? Yeah.
Sir, one question, sir.
Yeah, Vishwanath. Yeah.
Sir, you actually showed that figure, na? You developed that one.
Experimental setup.
Yes, sir.
Yeah.
Sir, once show me that one, sir.
Just a minute. 1 minute. Yeah, are you able to see the screen now?
Yes, sir. Yes, sir.
Yeah.
At the seventh one is there, na, sir? Wire screen mesh.
Yes.
Why the inlet is designed like that, sir? We are again converting that flow into laminar flow, na? Why the wireframe is attached and the inlet is also designed like that, no, sir?
No, but by the time the fluid comes here, like at the nozzle side, it's almost that portion, settling chamber portion is almost 1 meter.
Yes, sir.
So I am straightening the flow. Make sure that entire pipe will be with full of air. Otherwise, what will happen is some large turbulent eddies will form. At some location, some air will be there. At some other location, air will not be there.
Yes, sir.
So some screen will be mesh, like just like some mesh will be there. So it will straighten the flow. It will break if some large turbulent eddies are there. It will break those things and make it a laminar flow.
Yes, sir. I understand the wireframe. I'm asking about the inlet cross section, sir. That inlet cross section is designed in a very less area, no, sir?
Yes.
Makes teddies, no, sir. Again, again we are absoluting crossing the teddies again by the wireframe.
Yeah, that's what we're comparing different scenarios, like how with the so with a single thing how it is happening, with multiple things how it is happening. That is a part of our study only.
Okay, sir.
Again, we are changing the turbulent intensity. Like finally, our intention is to improve the heat transfer performance.
Okay, sir. Thank you, sir.
Yeah.
Okay. Thank you, Dr. Pularao.
Okay, sir.
Can you stop your sharing? I want to share my total all the sessions feedback.
Sir, 1 minute, sir.
Yeah,
Yeah.
gonna say.
One question is posted in chat box, sir. Can you please explain that?
Just a minute.
Yeah, Hari
So for
Krishna.
calculating Reynolds number, which diameter we need to take? Diameter of nozzle or hydraulic diameter of plate? Actually, it like whatever the literature they are telling, we have to use the size of the orifice, not the size of the plate. So we have to go by literature. Whatever the previous researchers have mentioned, we have to go by that size only. So they have mentioned that orifice size only we have to take. Does it answer your question, Hari Krishna? We
Yes,
have
sir.
to take
Yes, sir.
diameter of the orifice only.
Okay, sir.
Yeah, I think if there are no questions, so I'm ending the session, sir. Can I leave the session, sir?
Yeah, you can leave.
Okay, sir. Thank you, sir. Thank you.
Yeah.
Okay.
But that presentation you can stop. I will
Yeah,
share.
I have stopped it. Okay.
Right. Yeah. On my screen, is it visible to you, all the participants? Hello.
Yes, sir.
Yes, sir. Visible.
Yeah. So this is a total feedback which I received from the participants for all the sessions. First 9 sessions, and the 10th session I just now I will post it based on that will take. As of now, I asked 3 questions relevant to this total webinar. One is how would you rate the speaker of the each session? Then we got a very good response for all the speakers, as well as the next question is how helpful the content of the session to you. So whatever the content the speakers delivered on the topic of thermal management in electronic equipment, most of the people they have given, and we reached 90% of content it is delivered to participants. And the third question is how would you rate the overall satisfaction of session? So overall, both the presentation of the speakers as well as timings and in all aspects, communicating the details. With respect to that, we reached 91% satisfaction from the participants. This is all about the feedback which the participants gave to this program. This is for your information. We reached about 90% of on in all aspects from this webinar. Okay, now yeah, now I request, now I am posting the 10th session feedback link. Just go ahead and fill it, and after completion of this within a week time, we will send to your mail the participation certificate based on your feedback. Who are all submitted, for them only we will issue. That is the commitment we have done. Okay, and we based on that we will issue participation certificate. Now I request our chairman, head of the Department of Mechanical Engineering, to give finally conclude the session. And just before that, I request participants to speak few of you. Participants, you can speak. Okay, if there are no concerns from your side, then now I request our chairman, head of the department, to conclude the session.
Good evening to everybody. I think this webinar was successful because the because of the feedback given by the participants, and we have, I think participants have responded very well to the speakers, and we had wonderful speakers, and I thank organizer Dr. B. Kondareddy sir for organizing this webinar, and thank you one and all. I think we have reached your expectations. Thank you one and all. Thanks.